Hey everyone, in this AP Chem series video, we'll take a look at the connection between the concentration of a solution and its color. First, remember that there's lots of different ways to measure the concentration of a solution. In AP Chemistry, we use molarity. This is the moles of the solute divided by the liters of the solution. If there's less solute present, you're going to end up with a lower molarity because that solution is less concentrated. If there's more moles of solute, you're of course going to get a higher molarity. In this video, we'll take a look at how we can measure these concentration values using the color of the solution. To measure the concentration of a solution using color, first you need a solute that actually changes the color of the solution. And not all solutes will do that, but some of them will. Typically, these involve transition metals like iron, copper, nickel, or cobalt. The general idea behind it is actually a pretty obvious one. If you've got a darker color or a more intense color in the solution, that of course means a higher concentration because there's more solute present. Here in this series of copper sulfate solutions, you could imagine that the lighter blue color means there's less copper sulfate and a lower concentration, or the darker blue means there's more copper sulfate and a higher concentration. Most chemistry labs have a special device that can make this process a little more precise. Solution color and concentration can be precisely measured using light that's shined through a solution using a tool known as a spectrophotometer, and there's lots of different types. They sit on top of the lab table and look generally like the one shown. So here's what a spectrophotometer does. The first thing we need is a special type of glassware called a cuvette. You can imagine a very tiny test tube that is rectangular in shape. Inside the cuvette, you add a colored solution that you want to test. Here we'll imagine a 1M copper sulfate solution being added to this cuvette. I represented the solute particles dissolved by drawing in 6 little dots of copper sulfate. Once full of solution, you'd put the cuvette into the spectrophotometer. The spectrophotometer shines light through the solution called the incident light. This incident light has to be of a very specific color or a very specific wavelength that your particular solute will actually absorb. For copper sulfate, since it's a blue colored solution, blue light would be a very bad idea. That's why we see blue when we look at copper sulfate solutions, because they do not absorb blue light. So something other than blue, like the red light being shown here, might make more sense. When that incident light passes through the solution, those solute particles are literally going to block some of it, not all of it, but some of it from passing through. We describe this as being absorbed. So those solute particles will absorb some of the incident light as it passes through the solution. The light that does make it through the solution is called the transmitted light, and I've got that shown as a lighter red color to represent the fact that some of the incident light was blocked, so less light comes out the other side. Lastly, the spectrophotometer uses a photodetector to measure the amount of light that's been transmitted and feeds this to a digital display and a numerical quantity that tells me how much light was absorbed by the solution in a quantity called absorbance. Here we get a value of 0.43 for a 1M copper sulfate solution. It's a good idea to take some time and write down a few notes about how spectrophotometers work. So let's keep that first experiment in mind in the top right-hand corner as I reset my spectrophotometer for a second test. We're going to repeat this experiment, this time with a higher concentration 4M copper sulfate. I've represented the increased concentration with about 4 times as many dots inside the 4M copper sulfate cuvette. The point is that the increased number of solute particles are going to block or absorb more of the incident light. That also means that less light is going to be transmitted through that solution, so my photodetector reads a higher absorbance value, this time 0.61. We can put these two experiments side by side and summarize this by saying higher concentration solutions will absorb more light and transmit less light, another one of the key ideas for this video. Let's reset my spectrophotometer and do one more test, this time with a longer path length. The path length is the distance that the incident light travels through the solution. To test that, we would need a longer cuvette. As that incident light passes through the longer solution, it's going to come in contact with even more solute particles, so more of the incident light is going to be blocked. This means we're going to have even less light transmitted through, and my digital display is going to read an even higher absorbance value, this time 1.2. Let's put these two experiments side by side and summarize by saying that longer path lengths will absorb more light and transmit less light, the final key idea for this video. That also concludes this video on concentration and color. Thanks a lot for watching. Here is a brief summary.